Good evening, y'all. Wow, a little late on the start there, huh? When I said starting now, I hope you all understand by this point it's a soft now. Hi, it's good to see you all again. Hi, Thomas, good to see you. Yeah, back after a couple of weeks off. Sorry for the slow start. Had to make sure my wonderful dog Winnie got all of her dinner, because otherwise she is just a nightmare for the rest of time. She's great normally, but if she thinks she is owed food and doesn't get it, she is a nightmare for the rest of time. Let me adjust a camera here. I feel like I'm really out of the swing of things, right? Like I feel like I had this muscle memory that I didn't know I had, and now I'm like, how am stream? How am voice? How talk microphone? Chris, hi, good to see you. Chris reminds me that tonight I'm drinking, well, I'm hydrating, I suppose. But also, tonight's beverage of choice will be a Noon Whistle Hop Prism Blue India Pale Ale, which I think will be very tasty. It's a little stronger than I thought it was when I pulled it out of the fridge, so that'll be quite interesting. Yeah, we'll see how that goes. Ooh, let me know how the stream quality is looking. I'm just looking over at like my statistics over here, and it looks like it went from like 4 to 1 to 4. So like if it's stuttering, if it's being a little bit haywire, let me know, and we'll see if we can fix things. Like I say, it's been a few weeks, so it's possible I've screwed something up in the meantime. Or maybe YouTube has. Who can say? Tonight, y'all, I thought we would do a little bit of a curveball from things we've been talking about typically. I know it's like mostly been like DMX 3D printed moving lights and other DMX things. The winch project that never ends I'm still working on. I'm still working on the project in the background, sort of slowly but surely. There's been a lot going on at work, so I've been focusing a lot of energy there. It's also, as I'm sure I have mentioned before, it is the summer season, and our wonderful dog Winnie, who I love her to death, she does not like loud bangs, which includes thunderstorms and fireworks, so this is kind of a hard time of year for us. We were actually out of town for the 4th of July weekend. We rented a little Airbnb like an hour and a half outside of the city of Chicago where we live. A whole Airbnb house with a basement. We all just hid in the basement with her whenever there were fireworks outside, which is pretty much constantly for those 3 days. So we love her to death, but it's good to be back in the swing of things here with you tonight. I know, Thomas, it's really, we adopted her as a rescue when she was about 2, and we don't know what her history was before that, but we think maybe she has some like traumatic, thundery, boomy experience in the back there, which is not super great. So we just take as good care of her as we can. She got lots of like calming CBD treats and a thunder jacket that like swaddles her up real tight, which is really cute. So we just do our best and take good care of her. But now we're back, and I thought I would share with you. So like I say, working on the winch project, waiting on some parts to be back in stock at JLC PCB to order the next phase of the Demilight boards. Now I don't know how long we'll be waiting because as we all know, the chip shortage is kind of a wild thing in the world right now. And sometimes I'll look and be like, oh, I see our parts are in stock. I should order them when I get home from work. I get home and they're backstocked for another 11 weeks or something. So I've kind of put that on the back burner for now, just because it is such a slow process. But what I thought I might do tonight is share with you a little bit of the other nerdy things I've been doing in the meantime related to electronics and specifically related to amateur radio. And before you're all like, well, isn't that just for like old nerds? No, it's for young nerds too. And if you've never heard of it before, I'll give you a brief overview of what it is and why I have such a good time being an amateur radio operator and playing ham radio. It's a wide and deep hobby of very many things. And it means lots of different things to lots of different people. But I'll tell you, my focus in it has to do with like electrics and electronics, as you might imagine. And so I'll tell you about some of the fun parts of it that I've been up to in the past few weeks, including playing with some new transmitters, playing with some new receivers, building some large-scale antennas. You can actually see behind me here, probably a little out of focus, this big like hoop thing that's hanging in the background. That's actually an antenna that I'm currently in the process of building that's requiring a tube bending jig and a blowtorch to build. So we'll talk a little bit about how that's going tonight. Broke Both, hi, good to see you. It's been a little while. Just telling people how enthused I am about like some of the side projects I've been up to, including some amateur radio pursuits. Because as you all know, I'm a multifaceted nerd. I know we've been talking DMX for a long time, but I would just as I ease back into the swing of things after a month away from streaming, which is a weird thing to say because I still don't consider myself a streamer. I'm just a nerd who likes sharing things. But frankly, I missed all of y'all. I was like, I haven't talked to Thomas. I haven't seen Broke Both in the chat in like a month. That's weird. So I thought I would just share with you the nerdy things I've been doing. I haven't really planned like for any methodology of like how to explain what ham radio, what amateur radio is from like the ground up. So I don't have like slides or anything. So I'll try and do my best to give you context for all of this. Just when I say like, oh, this capacitor, that capacitor, which we'll look at in a little bit here, is rated for 10 kilovolts, and that's really important because I'll try and give enough context for the electrical theory behind the amateur radio, which is what gets me so excited, so that we can all appreciate, like, ooh, we really need to have a 10 kilovolt rated capacitor because the high power and such, and we'll get there. But yeah, that's what I thought we might do tonight, just to take like a little swing at something different. And I thought of this idea about an hour ago. I was like, yeah, we should get together on that stream thing and talk about amateur radio tonight. So let me do what I can off the top of my head to explain for those who have never heard of it, thought about it before, what amateur radio is. It is a hobby of hobbies. It's a huge, wide swath of things, but there is one particular chart. Let me get the portable keyboard here. That'll make things a little bit easier to show off. You don't need to see the keyboard. That's a little silly. ARRL frequency chart. I can see I've Googled this many times. Thomas says, I plugged in a motor today from the 1950s table saw that had been sitting and resting for 25 years and fired it up and ran smooth as silk and pressed. Ooh, that's a cool project, Thomas. Yeah, it's amazing how, like, built like a stone house those old motors were. I think I've told the story on the stream before of the wax cylinder gramophone project I was working on for the science museum that I work for. We had that back out actually a couple weeks ago for some guests that were coming in, and I was once again struck by, like, it's a cast iron motor housing with, hand wound copper coils, and other than some oiling, it runs just great all the time. It's funny, my boss took a look at it. He's got much more of a machinist's background than I do. And he said the first thing he said is, oh, it looks like my Bridgeport mill. And it does. It's built like, it's solid steel and aluminum and cast iron, and it's really just built like a tank. And these things just last. So it's always cool to get our hands on them. Let me see if I can find a decent image here that I'm trying to find. Yes, okay, that'll be good. So let me take you over here. So we'll just do like a real brief. To be fair, I don't know if any of you usual nerds out there care about amateur radio. I just want to give you a little context so I can get to talking about high power, high voltage applications. And actually, some of the interesting parts are the low power applications of amateur radio. But let me give you a little context if you'll humor me, and hopefully some of my enthusiasm will translate into clear explanation. So we'll see. So what is amateur radio? Well, amateur radio means different things in different countries, to be honest. But here in the States, can I full screen this? Wouldn't that be cool? Is it F11? Is it Command? Full screen, full screen, full screen. It is full screen. There we go. Yeah, there we go. It's like I planned it. At its core, like at its most base level, amateur radio is a license to emit RF energy, radio frequency energy. You may have seen, like, on the bottom of your phone, actually, or on like a USB charger. Let me see if I have one here. Yeah, this will be a good thing to look at. So here, I like everyone these days, I have 100 of these little, USB charger bricks from all kinds of things. And I'm, of course, way overexposed. Let's see if we can turn that down so we can actually see what's going on here. But on the bottom, this must be an Apple charger, or at least it claims to be an Apple charger. I suspect this one is a knockoff, but this one actually might be too small to have the information on it. Basically, any device that's oscillating with an RF frequency. Yeah, I think this one's too small. Let's see here. You'll often see, there's some exceptions for very small devices, but you'll often see, now I'm just casting around for power supplies in here, a warning on the bottom of your electronics device or on a computer charger or something like that that says, this is FCC Part 15 permitted to, do such and such and such. And really what that is, that means that electronic device has some part in it. And if it's a power supply, it's usually part of the buck boost circuitry that's generating your 5 volt or 12 volts or whatever it is output. That's oscillating at a frequency where if it emits too much radio energy at that frequency, it could cause problems for other electronic devices about it. And the takeaway is that every bit of the electromagnetic spectrum, at least here in the United States, and actually by international agreement around the world, is regulated by some kind of license, right? You cannot just willy-nilly emit radio frequency energy at any frequency without it falling under the purview of the FCC here in the States, the Federal Communications Commission, who says what amount of energy you are allowed to emit in any particular part of the radio spectrum. There are, it's not to say you can't emit any energy. There are certainly parts of the spectrum, like, for example, if you've ever used the little devices that you plug into your phone and they allow you to transmit to the radio in your car at a certain frequency, you tune your car radio to, 970 AM, and you plug it into your phone, and now you have a little tiny local radio station coming from your phone at 970 AM. That device is probably putting out 100 milliwatts of power, maybe 50 milliwatts, and falls into a part of the spectrum where the FCC says, okay, if you emit less than, half a watt, we don't really care, right? And there's exceptions like this all over the frequency spectrum. Like if you emit a very, very small amount of power, as long as you're not causing interference to anybody, and that's the big thing. As long as you're not interfering with someone we've sold the rights to that band of frequencies to, we don't really care. And Part 15 exceptions fall into that, too. That's what you see on the bottom of your power supplies. As long as you're not transmitting harmful interference, we don't really care. Amateur radio is a license to put out a lot of power over a wide variety of frequencies. So I have an amateur radio license. They are in 3 species here in the States. You have technician, just sort of your introductory license, your general, and your extra. These have changed over time, so this chart actually has a few more listed on here that were deprecated over the years. But basically, to get each of these licenses, all you need to do is pass a multiple choice question test. Technician is 35, I think general is 35, and extra is 50. That sort of become increasingly more difficult in terms of their technical knowledge and your knowledge of the spectrum and the laws surrounding this and all that. And they give you increased access to how much of these frequency bands you're allowed to put out energy on. And there are special rules for special bands, but for example, because I have a ham radio license, I can transmit, and I don't know how well this is actually going to show up, I can transmit between 7 and 7.3 megahertz, what we call the 40 meter band, or the 7 megahertz band, between 14 and 14.35 megahertz, between 18.068 and 18.168, this little tiny slice around 18 megahertz, and up and up and up from there. We also have some very long wavelength bands. 135.7 to 135.8 is the newly released 2200 meter band. And when I say that this is the 40 meter band or the 20 meter band, that's literally the wavelength of the electromagnetic radiation at that frequency, right? So we're all sort of, I imagine, familiar with the idea that the electromagnetic waves travel at essentially the speed of light, and so if you know the frequency of how fast your signal is oscillating, you know how long in distance that bit of radiation is going to travel in one cycle of its radiation. So if you have an oscillator oscillating at 7 megahertz, then at the speed of light, something that is changing 7 million times a second will go 40 meters through free space before it returns to the level of radiation that it started at, right? And like I said, there's lots of little weird exceptions for various things. You can only put out so much power on the 220 meter band. You can only put out, it can transmit in certain modes in certain parts of the band and so on. But basically, ham radio is a license to put out power in these chunks of the frequency spectrum, and quite a bit of power. I am allowed, per my license on most of these bands, to put out up to 1.5 kilowatts of RF energy out into the universe. And the interesting thing about this, I know, I said I was going to be like, it's just a short introduction to ham radio, and as you know, I don't have any short stories. But what else is new? The neat thing about an amateur radio license is that unlike a lot of other RF licensure, right, the license attaches to me, the person. So your cell phone, I have an iPhone here in my pocket, right? This iPhone puts out RF energy. That's how it communicates with the cell phone towers that it is communicating with. It also talks to my Wi-Fi. Oh, there's my wife and dog on my phone. It puts out Bluetooth. It puts out and various other things. And to do that, either Apple, who makes the phone, or the manufacturers of the individual modules, the Bluetooth chip, the Wi-Fi module in the phone, basically need to go to the FCC and say, hey, we've built a chip that we think that we guarantee adheres to your steps, to your processes, to how much power and how much spectral purity we're allowed to put out, and here's the test results to prove it. So the reason that I am allowed to hold this phone and connect it to Wi-Fi to download cute pictures of my wife and dog is that Apple has basically purchased a license for the amount of frequency spectrum that they need to do all those things, or their manufacturers have. In amateur radio, the license attaches to me personally and the devices I build and use. And I personally, by having an amateur radio license, guarantee that I am adhering to the various standards of power output and spectral purity and various things that the FCC says that I have to. For example, I am allowed to put out up to, like I say, 1.5 kilowatts, say, on a 7 megahertz frequency. But that signal, like any signal that's oscillating up and down, generates harmonics. So it's also putting out a little bit of energy at 14 megahertz and 21 megahertz and 28 megahertz, sort of the multiples of that frequency going up the spectrum. And as an amateur radio operator, I am bound by law to guarantee that those harmonics are at least 43 dB, 43 decibels below the primary signal. Now, decibels, for those who haven't run across them before, are essentially a measure of logarithmic power that we use to talk about very large and very small scales of power. You can imagine in a system, if we look back at this chart, we can see we care about things down at the 1 watt level. We care about things at the 1500 watt level. And so if we have to keep talking about things in ones and tens and hundreds and thousands of watts, the numbers just become so big or so small as to sort of lose meaning. And so instead we talk about things in terms of decibels, where 10 decibels is a factor of 10 multiplicatively. It's defined as the log of the ratio between your two powers. So 10 decibels is a ratio of 10 between two powers. So if I go from 1 watt to 10 watts, that is 10 decibels of change. If I go from 1 watt to 100 watts, that's 20 decibels of change. 1 watt to 1,000 watts is 30 dB, 30 decibels of change, right? You can sort of see how we turn a product of a process of multiplication into a process of addition. That's what decibels are about. And you see decibels in a lot of different fields, right? You see them in anything that has sort of a wide dynamic range. You see them in sound processing and audio processing, because in absolute terms, the range of human hearing in terms of like the amount of energy imparted to your eardrum to hear a sound is huge. You know, it goes from, nanopascals. I'm going to get the units wrong because I'm used to thinking of them in decibels, but it goes from little tiny bits of pressure to lots and lots of pressure. And so rather than saying, this is our unit of sound and now I have 10 million billion units of sound, we can say this sound is 80 decibels larger than the other one. It just shrinks those orders of magnitude down to numbers that I'm more comfortable talking about. So I have no short stories. So this is a long way of saying that, like, because I am the amateur radio operator in this case, I am guaranteeing that all of the harmonics of my primary signal are at least 43 decibels. That is 20,000 times less power than my primary signal. And I need to have filtering in place or measurements in place to guarantee that that is the case. So I find that concept really interesting, right? That almost all of the devices that we use that emit RF energy, the license attaches to the manufacturer, right? Or the owner of the IP of this device. But in the case of amateur radio, it is literally attached to me. If my devices are misbehaving, I am the one responsible. Now, this is not to say you can't purchase commercial equipment for amateur radio, right? It would be a little bit silly if every single thing I had to use, I had to personally build and verify. Although for a lot of the history of amateur radio, which started in the early 1900s here in the States, really when radio started, that was the case. You built all of your own gear. There was no commercially available gear. In the case of buying something, and I'll pull a couple out just to show them off in a sec here, because they've been fun toys to play with. Basically, the manufacturers are, really guaranteeing strongly that like their radios will conform to all the things, so you don't need to worry about like testing every transmitter to make sure it has the spectral purity you need, which is great. And all the reputable manufacturers, I'm sure, certainly do. But ultimately, the onus is on me, the license holder, to make sure that it actually does. This actually caused a bit of a foo-for-ah in the past maybe 5 years. There's a really cheap brand of like walkie-talkie style radios. There's actually several brands now, but Baofeng is sort of the one that you hear about the most in this community, because they do not live up to the spectral purity standards that the FCC requires. And ultimately, it is not necessarily illegal for Baofeng to sell those radios to amateur radio operators, because the licensure attaches to us. It's up to the license operators to make sure that those products, that we're following all the rules. Now, should they be selling products that they are fully aware at this point don't adhere to those standards? Probably not. But that's sort of a hobby drama for another day, if you will. So that's what amateur radio is. It's like the tiniest slice. So with this license to emit RF energy, what the heck can you do with it? You can build your own transmitters and receivers, which is one of the things that I like to do. And like I said, I didn't prepare for this at all. So I'm going to have to grab some bins if I want to show things, which I do. So here, I've forgotten how all this streaming works, but you still don't get to look at TummyCam. Here, you can look at this interesting antenna transformer that I picked up the other day. Of course, because I'm on this mic and not the lav, I'll have to either shout or be quiet while I go and grab these bins that are just above me here. But hang on one second. Goodness, there's just so much here. As usual, it's kind of a mess in here. Okay. So, just to share some of the things one might do. Where are we? There we are. With an amateur radio license. I'm going to zoom way out for this one. You'll probably catch a glimpse of the messy parts of the workbench that I usually try and hide, but I think that's fine. So, what's in the box here? This is an HF. This is a radio amplifier project that I've been working on for a little while. That's actually an early prototype that's turning into circuit boards. And this really, part of the reason I love this hobby so much is it really was, in a big way, my into circuit assembly and learning about electronics. This is a very much bodged together bit of circuitry with a couple of transistors here and a couple of relays just super glued, or I think they're gaff taped onto this piece of copper clad. This is a circuit assembly technique, a circuit prototyping technique, where you just I took a Dremel and just carved the traces into this piece of copper clad board here, just etched them out and made a circuit on a circuit board, and now slowly over time I'm turning that into an actual PCB that I can use. This bin makes me laugh. This bin was just labeled modules for scrap, and it's just a bunch of experiments in electronics that I've built over the years, all related to ham radio and some other things. What is this? Oh, that's my old Q light indicator project that I was building for a time. More copper clad, more amplifier. Oh yeah, so this was an early transmitter setup that I built and then kind of abandoned. So this is a radio transmitter. This one in particular, it will do voice, will do single sideband. I mean, it probably doesn't do it right now because you can tell it's kind of a mess. But the idea that you could, so when I put this together, I talked to a guy in Missouri on a piece of wire that I extended out from this BNC connector here and strung out across a park, and had a really brief, kind of weak and crackly, but very actual contact with a guy in Missouri. And I was like, that's super cool. Look at this piece of scrap that I bodged together with my own hands, and we're talking across the country. So we have our oscillator circuit. That's a variable capacitor that I stole out of an old AM/FM radio with this big gear on it for the tuning, so that adjusts my frequency. I have my, gosh, if I can remember what all the parts of this are. Power came in here. This is my mixer circuit that takes the RF energy from the higher frequencies and mixes it up and down to the range of hearing, so you can actually hear what's going on. We have our, what is this? It's 3 resistors and some caps. That must be our our receive. What's the word I'm looking for? Impedance matching circuit. We have our little audio amplifier board down here, and I don't know. So I guess what I'm getting to is like, if this kind of thing is like, wow, look what I could do with my own 2 hands to bodge a radio together out of some parts and components. If that feels exciting to you, get an amateur radio license, because this is a really fun part of the hobby, being able to build your own kit and gear. And then there's just other experiments hiding in here, various bits of various other filters that are coming together. That was what does this say? That's a 20-meter bandpass filter. So that's a filter centered on 14 megahertz. This sort of filters out unwanted signals in that part of the RF spectrum. I don't know. I had a great time for many years with this as my primary electronics hobby, just building these things together, and then testing them. Right, and that was another big learning process for me, is how do you both assemble these and how do you assess whether they're doing the things that you want them to do. Is a big part of electronics development, and something that when you're working with something as fiddly as RF energy can be a real slog. And so that's a cool part of the learning process, I think. Well, I'm just rambling, but that's not new. So, what does any of this have to do with anything? I guess, frankly, I'll tell you. So this comes back to what I have been working on. What is sitting behind me here in the corner that I will figure out a way to get on camera some point tonight. Probably have to turn the work lights on to show it. Chris says, here you are communicating with people in other states. I'm happy to get an FM signal on my block for Christmas. Yeah, it is. It's true. Like the distance you can go, partly, Chris, I mean, part of the issue with a commercial FM or, a consumer FM setup is the antennas are really small. Typically, maybe you've got a nice big one, but the wavelength of what we think of as the FM frequency band, so like 87 to 108 megahertz in the States, I think, you really want an antenna that's like, so that would be like a 2.5 meter wavelength, and a typical antenna for a particular wavelength will be, if it's got a nice big metal plate under it, like your car antenna sort of sitting on top of your metal car body, it'll be a 1/4 wavelength long. If you have it sort of in free space, in free air, it'll be a 1/2 wavelength long. So, and that's why your car antennas, back in the day when you had like, the extendable car antennas that came up out of your car or were dangling off the hood for all time, were like, maybe 2.5, 3 feet long, because they're a 1/4 wavelength of, some wavelength that's right in the middle of that FM frequency spectrum. So a bigger antenna maybe will help. If you ever want to talk about antennas and transmitters, Chris, listen, I'm here. And it's what I've been working on the past couple of weeks while we've been sort of stuck inside in the rain, is this device. So this is a Fusion 360 model of the thing that is sitting behind me here. I'll just walk you through it, because I think this is probably a little closer to the the typical interests of this channel, right? It's assembly, it's soldering, it's lots of 3D printing, my goodness. So I'll just talk you through it. So this is going to be what is known in the hobby as a magloop, a magnetic loop antenna. And it actually is kind of the counter example to what I was just saying to Chris. Yeah, Thomas, so Thomas, you're segueing me in right good. So bigger equals better. Bigger and the right ratio of size to antenna is better. Certainly compared to like a little dinky FM antenna in your, portable FM radio, full size is better. You can go too big. It's really about being a certain fraction or multiple of the wavelength you're looking for. A 1/2 wavelength antenna picked up in the center, right, so where it's coming back along a wire to your radio from the center point of that 1/2 wavelength is really good. Or a 1/4 wave on top of a big metal plane acts like the same thing. What I'm working on is kind of the counter example. So this is an antenna. Really, this is an antenna that sort of bucks that trend. So this is going to be an antenna where the main receiving and transmitting portion is this hoop here, which is actually a hoop of, in my case, 5/8 inch copper tubing, like copper plumbing tubing that I bought at Home Depot and bent into a circle. And it has, I wonder if it'll just tell me, because this is a relatively accurate model of the thing that I actually built. I can't remember what the diameter of it was. It's got a loop area. Oh no, it's giving me the area of this cross-sectional face. I want to say it's I want to say it's like 12 feet was the ultimate circumference of this loop. So it's a little over 3 feet in diameter, so a fairly chunky piece of copper. But this is going to be so thinking back to what we were just talking about, right? So if I said that a quarter wavelength or a half wavelength is ideal, this is a circumference of about 4 meters. So you expect it to be maybe for like maybe it goes up to like a 30-meter thing. Basically, this antenna is going to be radically small for the bands I'm going to put it on. Normally, a antenna for some of the larger gotta expect the edge. See, Chris, because I did this as a profile here and then rotated it around an axis that's in the middle of this pipe, I don't think I actually have an edge to inspect. Can I just do this? I could go back to that operation, but I don't think I have the way to actually get that. So this is going to be for the what we would call the 20, 30, and 40 meter bands. And normally an antenna for those would be, so when I go out operating portably with, and this is fun, talking about extendable car antennas. I apologize that I don't have all these things ready to hand. Like I say, I'm kind of making this up as we go. But that's also, I think, not unusual. So, talk about extendable car antennas. Here's the big version thereof. Get up there. So there's going to be really no way to show this. This is an extendable whip antenna, right? So it's a telescopic antenna, much like your car antenna. It doesn't have a motor in it, obviously, like your car would, but you can see all the little extendable sections. But this will actually extend up to 17 feet. I think it's 213 inches from the stud on the bottom to the tip on the top when it's fully extended. Now, that's definitely not something... I don't think I could even fit it in this room, maybe diagonally, if I showed it all the way up. But that's the size of antenna you're typically working with for some of the frequency ranges that I'm interested in. And I'm interested in them because they're good for longer distance communication, right? When I'm getting to Missouri, or this weekend when I made contact in Washington or Connecticut or Oregon or even up to Saskatchewan, some of these frequency bands behave better in terms of how they reflect off of the ionosphere. And so there's certain frequency ranges you want to use for distance and some for nearby and so on. And often for those distance ones, you're looking at a big antenna like this when it's fully extended. So this magnetic loop antenna sort of bucks the trend by being quite a bit more compact. So the trade-off is between size and bandwidth. With that big extendable whip antenna, I can cover with a decent range of reception and transmittability and sort of matching to my transmitter. I can cover everything from about like 6 to 8 megahertz or 12 to 14 megahertz or various other things really easily. I got a wide range where I can sort of set the antenna up and I don't have to adjust it at all. The same way that like your car antenna, right? Unless you've got a very fancy car, and maybe you do, if you have a very fancy car, your antenna might actually change size slightly when you change frequencies on your radio, but probably not. Probably it's just using like one piece of steel whip and it's the same size and it's close enough to being the right relationship to the wavelength to Chris's whip or nayday. It's whip, Chris. It turns out it's whip. The radio antenna in your car is close enough to being the right relationship to the various frequencies you're interested in to be just fine. And the large whip is the same thing, just a different set of frequencies. This is very much smaller than the ideal length, and so the trade-off is you really only get a very thin slice of frequencies, right? With the larger antenna, maybe I would get from 12 to 14 megahertz. With this antenna, I would be lucky if I got from 14 to 14.02 megahertz. 20 kilohertz would be really quite wide. Probably it's going to be closer to 10 kilohertz at a swipe. So there's this truism in antennas is there is a trade-off between size, the physical size of the antenna, bandwidth, right, how much of the frequency spectrum in your area of interest you can cover, and efficiency, right? You could pump energy outside of that very limited bandwidth into this antenna. It just wouldn't really get out anywhere. It would sort of be, go round and round and round and be radiated as heat more than as radio frequency energy. So what this aims to do is sort of, because I don't have a lot of room being on the ground floor of a 3 flat here in the city of Chicago, What I'm instead sort of prioritizing is having a compact size with low bandwidth and hoping to still have high efficiency with the antenna. So this 12-foot hoop of copper pipe is sort of the first part, and the other key part is what sits in here, and this is going to be the thing that I think I have to try and show you physically because I don't have a model of it here. So let's figure out how that's going to work. Gonna be quite a thing. Maybe I can lay it on the table for a second. Nope. That's not gonna be a thing. Let's see, what might we do here? Can I use, I think I turned this other camera off. We could just, I could just Google an image of it, but that seems a little silly given that I've got one right here. Oh, I guess you can kind of, here, we'll hold it up close to this camera and you can see it. Yeah, Thomas, it's quite a contraption. And so this is our big copper hoop here. And this, you can kind of see the brand name comment on there. This is I don't know if you can hear me. Can you hear me? I hope you can hear me. This is a vacuum variable capacitor. We've talked about capacitors to death, I'm sure. This is an adjustable capacitor with a vacuum inside it. And it is adjustable via, I don't know if you can see this, we'll look at this in the model in a second because I imagine it's a little hard to see in this view here. There is a wooden dowel running down here that's secured by this mounting block. And like I say, I'm sure this is hard to see, we'll look at it in the model. But by twisting that, we turn this whole assembly, which is attached to a little post coming out of this plastic red part. And that's actually moving some components inside of the capacitor to change the capacitance of the thing in real time. Yeah? Okay, now you've seen it. Let me put this down for a little bit, and I'll walk you through it in the rendering. There is a really decent chance that that's gonna like slide away at some point, but you know, if that happens, it happens. So that capacitor sits right in here, right inside this 3D printed mount. And it's got a couple of bent copper plates that attach the top of the capacitor to this metal rod. You know what we should really look at? Let me pull up a data sheet for this, which I just happen to have standing by. Yeah, so that's, for those, if you couldn't see it on the camera, this is what it looks like. It's a Comet CVAB 500BC 5BAL. It is so for the size of it, right, you'd think it would be a giant capacitor. For comparison, if I pull out my bin of quote-unquote large caps here, pull that out, right, here is a cap that is... This is a 330 microfarad cap rated at 200 volts that I clearly pulled out of something ages ago, right? So this is 330 microfarads. This one we've been looking at in the project that's much, much bigger is 500 picofarads, almost 6 orders of magnitudes less capacitance in this vacuum variable one. So why it's a chunk, what I would call a chunky boy. It's like 2.5 pounds. Let's see if it says here how much it weighs. Doesn't look like it. But so why would we use this this giant... There's no fedoras in the... Chris, you're killing me. Why would we use something that's like big and chunky and so low capacitance? It's because of its high voltage rating. One of the characteristics of these magnetic loop antennas is that because they are so much smaller than the wavelength that you're interested in, they tend to be a very high voltage a high circulating voltage going around the ring. Normally, the voltage off the end of a sort of a full-size antenna would be, several hundred volts, like not nothing. And this is all related to the amount of power that you put in, right? So for putting 100 watts, which is sort of a typical, if there is such a thing, a typical amount of power for a hobbyist like me to use, either at home or portably. There's a lot of 100-watt radio products on the market today. For a 100-watt radio, you might have a couple hundred volts sort of present at the end of your antenna wire. For a magnetic loop like this one, it would not be uncommon to have 3,000 or 4,000 volts present at various points on the loop itself. So we need to use a very high voltage rated capacitor that's able to handle those kilovolts of potential across it. So that's what's mounted in here. That capacitor has, and it probably will be easier to see on this datasheet than it was in person. Yeah, here's a little drawing of it that was very helpful in making the 3D printed model. Has this little stub coming out the top, and when you rotate it, it actually changes the capacitance of the capacitor. In fact, I think there is a chart here. Yeah. So for how many turns between 0 and 15-ish turns before it hits its stop at either end, it goes from about 0 to about 500 picofarads. Which is a quite significant range. That's 2 orders. Well, if you don't count 0, if you count from, say, 5 to 500, that's 2 orders of magnitude. That's really quite good. And it has this little stud poking out that you turn to make that happen. And what that stud's doing is actually rotating a screw thread inside the device. Oops. And we're adjusting the capacitance by moving 2 concentric shells of copper in and out of each other, and the more they overlap, the more that surface area of those 2 plates overlaps, the more capacitance you get, and the less intermeshed they are, the less capacitance you have. And they're all surrounded by vacuum, because vacuum tends to inhibit the creation of sparks between your plates of your capacitor, right? Air becomes ionized at a relatively low value of voltage, right? You can create a spark in air with, several hundred volts. In a vacuum, you need, for a given length, maybe, 6 or 7 times more voltage in your medium before electricity will jump the gap and cause your capacitor to fail. So that's why we use a vacuum variable capacitor. It's just so that we can go to higher voltages in a smaller space without things arcing over and causing sparks. So that's what that part is. Then we have this tuning mechanism, which uses this sort of 3D printed adapter. Let me bring that up there. And a sort of mount to hold it in place. This is a wooden dowel as opposed to like a metal rod or something else, just because it's non-conductive. So any metal, especially metal that's inside of the loop where sort of the action is for this antenna, will detune it, will cause it to be less efficient. So using plastic and wood in here is really nice. So I have this wooden rod extending down here. It's going to couple, this actually is the newest part of this project, it's going to couple to another wooden rod to make this all longer. I actually just printed this the other day. It might need another revision, as these things always do. But this is the coupling portion. It comes in these 2 pieces here. The idea being that there is one dowel that is permanently mounted to the antenna, to the capacitor there. That will have this piece on it, sort of as the coupler piece. And then there'll be a second piece, a second dowel that extends the coupling quite a bit lower to make it easier to access. But that piece is going to be a little bit unwieldy to leave on all the time. So the idea is the second dowel will have this piece on it. And when I need to tune the antenna, we'll come in, we'll mate the 2 together, we rotate and clamp. And now the sort of tongue of this second piece attaches to the first one, and I can use the second dowel to rotate the first dowel and accomplish tuning. And then presumably when I'm done, disattach them. And this is where it's a little bit tight. That's where the second revision comes in. And take that second dowel off so it's not flopping about. You can see in the drawing here, so here's that coupling link, the little mount it'll mount on, and the dowel extending down to a little handle that I have yet to print. So I can rotate this handle, that'll rotate this dowel assembly and adjust the capacitance on the capacitor. Is the idea anyway. We'll see if that works. The other significant portions here, some 3D printed parts to handle the mounting of the 2 different loops. This smaller loop is actually not part of the transmitting part of the antenna. This is just so we can sort of couple the signal from the transmitter into the larger loop. This accomplishes an impedance transformation. And this is getting into the kind of the weeds of RF a little bit here. But basically, you have maximum power transfer between a transmitter and a load, an antenna, or whatever your load is, when their impedances are equal. Impedance, you remember, is the complex form of resistance, right? So we're talking about resistance being in ohms. Use Ohm's law with voltage and current to deduce, how much current is flowing, how much voltage is present, how much power is being consumed. Impedance, exact same idea, but now we include the concepts of inductance and capacitance to form a more complex view of what's happening to the current inside of your system, inside of with your transmitter and your antenna and so on. Oh, Enrico, hi! Not sure if the brain space to stick around much. Totally fair. Dropping and saying hello and avoiding work. Enrico, thanks for stopping by. That's very nice of you. Yes, I said it. I said at the very beginning of this, this is a total departure from all of the things that we normally do here. I just wanted to share some of the nerdy things I've been making for the past few weeks, and just put out more nerd things into the universe, because I feel like pretending that I'm a single track nerd, which I wish I was. I wish I had one thing I was interested in, but no, I'm interested in all kinds of things. So I'm just going to share them here, and it'll be great. So thanks, Enrico. Thank you for stopping by. It means a lot to me. Let's see. Impedance transformation. Oh, the long and the short is you want your DMX over ham radio. Wow, that would be a wild ride. So part of the thing about ham radio, actually I should have said, thank you, Enrico, and we'll get back to impedance transformations, which I know you were all on the edge of your seat to wanted to hear about how impedance matching works. I could tell, I could feel it out there. Part of the thing about amateur radio is that it is amateur. You are actually not allowed to do anything commercial over the ham radio frequencies, with a little exception carved out for you can talk about commerce related to hey, can I sell you my amplifier? Can I sell you my antenna? Hey, I want to buy the commerce related to the actual product of amateur radio. You could do over the air, but you can't use it to broadcast a show or have commercial messages or transmit music. Although the music thing is fascinating, there is specifically an exception carved out in amateur radio for in the States, at least. You're not allowed to transmit music because that would be potentially somebody's commercial work or your own work, except the International Space Station has a couple of amateur radio transmitters and repeaters on it, so the astronauts can actually get on the radio and talk to people. But also there's a system where you can essentially bounce signals off the International Space Station, and because they don't want to put unnecessary burdens on the astronauts on the ISS, if the astronauts on the ISS have music playing in the background and it gets transmitted over the air on ham radio, the astronauts are explicitly not in trouble. It's fine. It's music, transmitting music is forbidden except for incidental transmission by the International Space Station. It's carved out in law by the FCC. I love it very much. Enrico says, should on this, but never finished my ham radio course. Oh, Enrico, listen, if you ever want a buddy to get back into it with, I'm here for it. Yeah, it's pretty neat. So could you do DMX over ham radio? You could. You couldn't do it for any kind of commercial purpose. So you couldn't use it to drive things for a show. But people do use these licenses for things like if you're flying model airplanes, right? If you're a member of the public, you're sort of constrained by the radio licensure around what people are allowed to sell for controlling models, right? Which is 5 watts of RF energy. If you have a ham radio license, as long as you're not doing this for profit, which most people flying model planes these days, I imagine, are not, you can use the ham radio frequencies to control your planes and put out, tens or hundreds of watts if you want to. Now, if you are a drone pilot, say, and you're flying a drone around to get photography for a business or something like that, that is explicitly a commercial purpose, and so you would not be able to sort of use your privileges as a ham radio operator to do that kind of thing. So the really interesting, listen, this is all just freeform. There's a really interesting thing that comes up very often because hams have been doing this for a long time, since the early 1900s, and sort of came up with technology as technology advanced. And one of the sort of obvious use cases for people who are interested in radio transmission and communication and linking people together these days is the internet, or an internet-like network. Whether it's connected to the internet as a whole, or whether it's just, I have a computer at this site. I want it to talk using something that looks like TCP/IP to a computer over there. We've got some antennas pointing at each other, but it's not hooked up to the internet. Either way, that would be a really cool thing to do, and lots of people do this. There's some very cool projects out there by an organization called TAPR, the Tucson Amateur Radio Conference, I think. Tucson Amateur Packet Radio, it must be, because this is back in the day of like message boards and packets flying back and forth. Or the Amper project, which does sort of emergency preparedness version of this. But it's all to say, one of the interesting questions that come up is, can you use encryption to transmit these messages? Even very basic encryption, like using HTTPS, like using SSH to transmit a file securely from one point to another. And there are one of the exigencies of amateur radio is you are not allowed to use codes which obscure the meaning of your message, right? This is not meant to, and this is related to the non-commercialization of the thing, right? They don't want people using amateur radio because it is carved out for amateur experimentation. They don't want people, the FCC doesn't want people to come up with some clever codes to do some interesting things which might allow businesses to hide their interests on the amateur frequencies. So can you use something like SSH to, securely transmit things? Well, it does obscure the meaning of your message, right? No one else but the intended recipient can tell what that message is saying. They can tell that it's probably TCP traffic. They can tell that it's encrypted using an SSH scheme, but they have you obscured the meaning of the message in a way that is illegal? Measure of constant debate. Enrico says, big reason for me to start the course is disaster response. And field tech and ham is a big part of that. Yeah, there are people whose whole interest in amateur radio is, like you say, Enrico, emergency preparedness and emergency response. Whether that's just having what we would call a handy talkie, like a little like a walkie-talkie style radio. I actually got one just here. Right, so you might have a radio that looks like this. Looks a lot like a walkie-talkie, but it transmits on the amateur radio bands. That you might go out into the field with and help with a search and rescue team that's trying to find somebody, or help with fire response. I have a bunch of friends out in California who are dealing with this season's wildfires, and so being able to communicate with some decent amount of power and some understanding of antennas and battery systems and solar power might be a really useful thing to have. There are also, organizations that specifically prepare for natural disasters. ARES and RACES are the two big ones here in the States. They are, ARES is the Amateur Radio Emergency Service. I think I've got that right. And they do, sort of drills and preparedness to say, like, okay, if there is a natural disaster, in California, it's wildfires and earthquakes. In the South, it might be, a hurricane. If one comes through, we will have a team of people that we've gathered together who will be trained in using communications gear to, go out into the community and find people who need help and help communicate from those people back to medical services, rescue services, legal services, whatever they need to do. Is a big part of amateur radio. There's also, so ARES is the sort of amateur service. RACES is, I don't remember what the acronym stands for, but they're affiliated with the military side of things. So they are funded and organized by the U.S. Armed Services, where ARES is sort of managed by amateurs. They coexist side by side. Anyway, that's it's another sort of facet of amateur radio, which I find fascinating, and is super valuable to a lot of people in a lot of areas. Let's see. Is there anything more to say about this antenna thing? Oh, we were talking about impedance matching. In any case, really, because this is such a short loop of wire. What's a good way to explain this? Because this is such a short loop of wire, at the frequencies we're interested in, this loop of wire looks a lot like a short circuit, right? So at the end of the day, what we're going to do is, what we could do is connect the sort of two sides of our transmitter, the shield and the center of our coaxial cable, to both ends of this copper. And for all intents and purposes, right, we've created a short circuit, a 12-foot long piece of copper short circuit between the two, the plus and minus side of our electricity, if you will. And so it's a very, very low impedance. I mean, in this case, we're talking about like milliohms, very, very low. And typically, transmitters, in the hobbyist world, in the amateur world, what they would like to see, what they're built to see, is an impedance of about 50 ohms, right? So we have this antenna that's at milliohms, and we have this transmitter that's 50 ohms. And so one of the ways we can sort of transform this short circuit into looking like it's higher impedance than it is using this coupling loop. You basically make two loops. It acts like a two-turn transformer, essentially. So if you're used to working with AC circuits and you're used to transformer action, we have a small loop of a transformer and a larger loop of a transformer, and that makes the larger loops, or transforms the impedance by the square of the ratio of their sizes. It makes us look a little bit more high impedance, gets a little bit more efficiency out of our transmitter system. So that's what that second loop is about. And some more 3D printed mounts to hold it all together. And then this sort of like 3D printed thrust bearing, which we'll see how well that works, because this whole thing is going to sit on top of a piece of 1-inch EMT conduit that's already mounted in my backyard, holding up some string lights. And the idea is that this whole thing is portable. So if I turn the PVC view off, if I turn where is my conduit? If I turn the conduit off, this is what is actually behind me here. This is what the whole thing that Thomas would have called a big boy, is this 6-foot stick of PVC that will hang with its antenna in my garage on a couple of 3D printed hooks, because of course. I might have those hooks here, but they're, they look like this. And so the whole idea is when I want to operate, I'll take them off the hooks in the garage. I will walk them into the backyard. I will climb a little stepladder, and I will pop this thing down into this 10-foot stick of conduit. And now this loop is at 11 feet off the ground, and height helps with a radio antenna. So getting it up a little bit, getting a little bit above my garage, getting a little bit higher above the nearby buildings will hopefully get me out a little bit better. So that's the idea of this antenna project. It's going okay, I would say. The biggest issue I'm having so far is trying to solder the copper adapter plates that go from the capacitor to this copper. I'm gonna get the big boy out again, and I'll try and show you and shout at you what the issue is. You'll see. There we go. So this is one of the top copper plates. So here's our two parts of our loop antenna, and then these copper plates that I sort of fabricated as adapters. You can probably even tell from there, the solder job on these is just atrocious. Like, it's really crusty and awful. This is all done with a blowtorch and some plumber's solder, trying to get these joints really to be secure. And they are secure. They're just not very clean. The other one is also, and it's better. What I really should have done is done a much more thorough job of bending this copper sheet into a perfect matching circle to match this piping before soldering it in place. Solder, as we know, does not like to jump gaps. You can see on that one I have a bunch of solder clustered on the end there. So I kind of casually bent it around the pipe and then tried to solder it, and it went fine, but it didn't really, adhere as cleanly as I would like it to. So I probably will have to take another stab at this whole thing. Maybe I'll just cut off the copper pipe there and make this a little bit shorter, and then reformulate these brackets. These brackets, I should say, they mount to the capacitor. Gosh, I don't have any way to show this. You can kind of see here, just with some screws. So the contacts of the capacitor are just these two plates at the end. They're meant to do exactly what they're doing here, is you screw your electrical contacts onto them. Because as you can imagine, right, if you're working with several kilovolts and maybe 50 amps, you need a big surface area to get that current to flow through, and so you literally just screw onto these end plates. Is the idea. Hang on. So some more things, some skills to build there. The blowtorch soldering went okay, but not super well. So I'm gonna have to work on that a little bit again. But yeah, that's the big antenna project that I'm working on now. That's been a lot of fun, and if I get results, I will certainly share them here. Some of the other things about ham radio that I've been getting more exposure to recently that I think might be interesting to some of you nerds are the battery systems that we get to use. So like I say, I live in a 3-flat in Chicago on the ground floor. We have a decently sized backyard, but we're between 2-3-story apartment buildings on either side. So really, if I want my signal to get out, I need to get out into somewhere that has more clear space, usually a park. We have a public park like 5 minutes walk up the way from us that I do quite a bit, or something more adventurous like a state or national park, for which there are activities where you get points for activating them, going out and working radio in these parks, which is a lot of fun. But to do this, of course, if you're going to work portably, as we would say, if we're going to operate portably, you need a battery system. And there's lots of different varieties of batteries you can use, but I thought I would share a couple of them because they're a useful resource for lots more than just amateur radio. So let me, like I say, I don't have them on the thing here because this is all spur of the moment, but let me pull a couple of them out. There's one. And there's the big one. So let's start with the little black one here. Chris, this might actually look fairly familiar to you. This is something that an idea that I stole from my time working in nonprofit theater. This is nominally a 12-volt 6 amp hour battery. This one actually has a couple of additional outputs on it. So this one has a 9-volt, I think 2 amp rated output and a 5-volt 1 or 2 amp rated output. But we would use these in theater all the time for their 12-volt output because we'd be driving 12-volt. Oops, excuse me. We'd be driving 12-volt LED products like LED tape from them. Let's see here. So the brand that you'll see all over the place, I think I got this one from Amazon, is Talent Cell. This particularly is a YB1208300 USB battery. Yeah, you can see the specs there. 12-volt, 6 amp max, but two 12-volt. So 9-volt at 1 amp, 5 volts at 2 amp. 100 watt-hours is what it claims. I have never really drained it all the way down on a load tester to see if that is true. But this is probably maybe a pound and a half. And it's a great little battery for doing portable operations with. A lot of amateur radio gear is expected to run at nominally 12 volts, or in reality more like 13.2, 13.6 volts, which is the voltage you might think of a typical 12-volt lead-acid battery. And that's not a coincidence. That was sort of the power source portably of choice for decades was automobile batteries, was 12-volt sealed lead-acid or lead-acid batteries. And so a lot of products are sort of spec'd to that voltage range, even if they're no longer meant to be used portably. So this one really is closer to 12 volts. I think it starts at about 12.4 and goes down from there. So it's not quite up at the 13.2, 13.6 that we would normally use. But this was, I think, $50 on Amazon. It's pretty portable. It's pretty light. It's a decent amount of power. So when I'm going for a really lightweight setup, this is great. They also make some smaller versions of this. So this is what is this one? The 100 watt hour, the 6 amp hour battery, 8 amp hour battery at 12 volts, I think. They also make like a 6 amp hour and a 3 amp hour. I might be getting those wrong, but basically you go down in size from here. You go a little smaller, a little thinner, and then smaller and thinner still. Great for hiding electronics inside props or costumes or tables or things like that. So that's where I knew this brand from. When I saw they came out with this sort of bigger model, I had to scoop one of those up. So this is my sort of lighter weight version. And then this is the big boy. This is my 12-volt, 12 amp hour battery from Bio-NO Power. And Bio-NO is a pretty well-known name in the amateur radio and the solar power sphere. They make these nicely packaged, nicely managed lithium iron phosphate batteries for a variety of purposes. They come with Anderson power pole connectors already on them, which is sort of the de facto connector standard. Guys, I don't know if we talked about it here. I love power poles. It is a great connector. They are durable. They are relatively easy to install. You can get them in a variety of power ranges up to 45 amps, and actually up from there, they just stop sort of being cross-compatible. Yeah, really great connector. If you don't know about power poles, really worth looking into. So this BioNA battery comes with power poles on it. It's also got a barrel jack where the charger comes plugged in. It's got a nice battery management system inside, and if you're working with batteries, that's pretty key. A battery management system says instead of just like, tacking a bunch of batteries side by side with the ends hanging off, you get a system on top that makes sure that they don't get overcharged, they don't get over discharged, that if you try and pull too much current, it'll trip a sort of temporary circuit breaker and say, hey, no more power until I cool down, essentially. And a variety of other protection features. And they package that all up in this nice little box. This weighs, I think, 3 pounds or so. And so, nominally, this is a 12-volt, 12-amp hour. This is a 6-amp hour. This one is definitely... it's a little less than twice as big. It was fairly expensive, but not horribly. So I think this is like $100, but it's a real investment, right? Like this, I'm going to use for years and years and years. 12 amp max continuous discharge current and 20 amp max peak discharge current. So I could put a 12 amp load on this for all day until the battery ran out, or I could pull 20 amps out of it for small amounts of time, which is great because my big transmitter pulls about 20 amps when it's cranked all the way up. For some of my smaller transmitters that pull, like 3 or 4 amps max, I'll use something like this because I don't need that full current capacity. Yeah, Chris loves the power pole connectors. They're versatile, they're durable. They don't, if you need a really tightly interlocking connector, they're not great, but interlocking DC and AC connectors are not super common anyway. And so I think the power pole is a really great option. And once you have the tool, so I do things like this a lot. This is something I just whipped together the other day as I was doing some experiments. This is just a real dumb and easy power pole squid. So this is 3 sets of number 10 gauge primary wire with some power pole connectors on the end, and then they're just into this block of Wagos. Wago is another super great connector. Lever lock is the generic name. Anything you shove into one of these and clamp down on will be connected to anything else on the block. They make them in 2, 3, and 5 wide connectors as far as I've seen. This is just 2 of them super glued back to back to make a sort of generic DC adapter. And the reason I had this is because I was doing some work that required me to switch back and forth between this battery, which has a barrel jack on it, and this battery with power poles. And so for the day, I just put a barrel jack into one of these lever lock connector points. It's like, okay, well, I can power this from power pole or barrel jack or both or neither, right, as I need to do. It makes it really easy to swap things out. It's a little unwieldy, right? Like, this is not great for taking in the field, but it's really nice for experimentation. So you can also... This is a nifty tool. This is well, it calls itself a high precision watt meter and power analyzer. I don't know that I would necessarily call it high precision. Well, that's not fair. I would call it high precision. I wouldn't call it high accuracy. It definitely does not 100% agree with what my power supply would tell me about power draw. But it's a really simple device. It comes with sets of power poles on either side. It has a source side where you plug into your battery or your power supply or whatever, and your load side where you plug in your transmitter or your radio or your squid of cables to put on other things. And it just tells you both instantaneously how much, what's the voltage on the batteries, what is your current power draw in amps and watts. And then it will also tell you your peak amperage, your peak watts draw, and your cumulative power draw over time, which is really handy. So for example, if I'm operating in the field and I have Big Blue over here running things, and this is a nominal 12 amp hour capacity, and I would love to have some warning before it just up and dies on me, it would be really handy to know how much of that power I have consumed, how much of the energy I have used. And so something like this will say, okay, so right now, receiving a signal, you're drawing a couple of amps. Total for this afternoon, you've drawn 7 amp hours. And so, okay, I have about 5 amp hours worth of energy left in this battery. Or equivalently, I could do it in watt hours, right? This is, nominally 144 watt hour battery. I could say, okay, I've drawn 60 watt hours. How much power do I have left in the thing? So, super nifty tool, the high precision watt meter and power analyzer. You can find these on Amazon as well or from other retailers. But I just like to show them off because I didn't know this existed for a long time, and I would just sort of have to hope and guess. Because unlike lead acid chemistry, where if you fully charge your car battery, with a 13.8 volt charger, your car battery with no load on it is probably like 13.6, 13.4 volts. And as that battery discharges, which hopefully it doesn't, but if you were to leave your headlights on and your battery discharges, lead acid chemistry is such that voltage goes pretty linearly down with the amount of energy remaining in it. So if your battery is half discharged, its voltage might be 11.2 volts. And when it's fully discharged and almost dead, it might be like 9 volts. Right? You have this nice linear gradient from fully charged to totally uncharged. Your voltage changes with available energy that's left. Lithium chemistry is not like that. Lithium chemistry, especially lithium iron phosphate, which is what this one is, you basically get your full rated voltage up until you've drained about 90% of the energy out of it, and then it just drops off a cliff. So you can't use voltage as a proxy for remaining energy. You have to do something that either tracks your energy uses over time or does something more clever to figure out how much energy you've consumed. You can't just put a voltmeter on it and know how you're doing. So anyway, a useful little tool for that kind of situation, I think. Also good for in the theatrical realm. You could use these if you were trying to see, when I turn the lights up this bright, how much power am I actually pulling out of this battery pack? Am I ever going to be pulling too much and damaging the pack? So that's kind of a fun tool. All right, I got 2 more things to show off, I think. So we talked. So we'll do the less fancy version of. Yeah, the power you got. This is the thing about lithium, Enrico, right? You get power, and then it literally just it drops from 14 volts to 11 volts, and then the BMS just cuts you off, and your radio shuts off, and that's the end of your playday. We were talking just a moment ago about impedance transformation. And making sure that your antenna sort of matches your transmitter. And this is one of the tools we use in amateur radio or something like this to see what our antenna is up to. This is actually a fairly old product. I picked this up at a swap meet for about $20. This is the RF Analyst model. RF1. This is what we would call an antenna analyzer. It's basically a device that measures the impedance of a circuit at a particular frequency. So how might one demonstrate this in a reasonable way? He said, not having prepared a demo. I'm trying to think what other. Wonder if the thing is, I don't have a great adapter to go on here that I could just hook a component up to. Or do I? Hang that thought. I don't know where my test card is for my vector network analyzer, which is the next thing I'm going to show off. Maybe I do. No, apparently I don't. That's a shame. I guess, to be honest, Enrico, I definitely do have that adapter. It's just a question of how many bins would I have to pull out to get the adapter. So this is what we would call a UHF connector or a PL or an SO239, and I wanted to plug it into something like a BNC. I was like, well, I have a UHF female, the BNC male I know in that bin, and I have this is the ASMR part of the stream. I have a BNC female to SMA. I go SMA to BNC male, and I'm going to twist. It just starts to get a little bit complicated. But I do have my big bin of adapters we could just rummage through. I just wish I could figure out. So I have a a test card. It's basically a PCB. Oh, stand by. Dang. I don't know where my test card is. Actually, I don't know where my VNA is either. It's probably out on the porch. I was using it to measure some antennas the other day. That's all right. This is all just, we're just spitballing everything anyway. Where is that test card? It was right here, I thought. And now, it's not. That's all right. I don't know. Well, here, if we're not going to pull out the VNA, we could at least pull out the big Bino adapters, which also is missing. Okay, so now we have a mystery on our hands because, yes, okay. So there's the VNA. There's the adapters. Does that mean that the test card also fell in here? We'll make our own demo out of this. So let's get rid of a couple of things. We'll move the batteries off the table. We'll move this box. We'll move this HT. And let us see about putting some shenanigans together. So as Enrico says, I do have quite a few adapters here, but how many of them are from UHF to something else? I need my UHF adapter kit. That would help a bit. That's a different antenna. This is UHF to, that's SMA to BNC. So there's all these different kinds of coaxial adapters for different frequency ranges and different amounts of power. And some of them are standard in some situations and some of them are standard in others. So let's see. So if I wanted to use, got this SMA to BNC, SMA male to BNC female. So let's put that on a BNC male to screw terminal. Enrico, thank you for believing in me, because I wouldn't have been bold enough to try this on my own. But there we go. So now we have screw terminal to SMA male, and now I have UHF to SMA female. Screw those together and move some adapters aside. And now we have our UHF to screw terminal. So now we can actually play with and do some things with that. So with that, we need some components to test. Let's see here. We've got some resistors. Let's see, we'll need some small capacitors. Interesting. Oops. Webcam's falling off the shelf. It's a whole thing. Need it to come in 3-pin. Yeah, you could adapt it to Edison if you were a real monster there, Chris. I think these are, what are these? Are these 50 ohm? I keep a lot of, those are 82 ohm. That actually might be interesting. So let's grab one of these 82 ohm resistors. And let me see if I have any 51s left in here. If I don't, I have a whole thing of them, but I, again, would have to go spelunking for them, and nobody wants that. 5100, 51K. What are you? You are... I think that's what I'm looking for. All right, so now we'll take our screw terminal adapter here. If you're wondering like what the heck's going on, hopefully it will become clear shortly. Our screwdriver and just open up these screw terminals real quick. And let's start with this 82 ohm resistor. So remember I said earlier that in amateur radio, the typical impedance that we're working with is 50 ohms. So our transmitters are expecting to see 50 ohms. The antennas are all, in theory, matched to 50 ohms. And the test gear should also be all matched to 50 ohms. So in theory, when I put an 80-ish ohm load on here, then for some frequency, the SWR, and because this is a purely resistive element, well, as much as a physical component can be, we should expect to see, even if we change frequencies, right? So this is currently at about 4.8 megahertz, and I can use this dial to dial it up and down. Remember earlier I was talking about how I was interested in like the 14 megahertz range. So like here, I could dial this up and say, all right, I'm interested in some frequencies around 14 megahertz. And then I could see what my resistance is, my actual resistance. This is 84 ohms. The inductance is 0.85 microhenries, which might be a little surprising if you're thinking about this in terms of ideal components, but it's actually the fact that this is a wire wound resistor, the resistive material around them, and those coils of wire cause this to look like a small inductance. 0.8 microhenries is not huge, but just a little bit of inductance, in parallel with about 130 picofarads of capacitance. And that probably is mostly from the fact that we're using this short bit of wire, the short bit of coaxial cable to connect to this component. If this component was right here at the tester, we'd probably see something a little bit different. But because this is, in theory, mostly resistive, I mean, we've seen it's mostly resistive. There's not a lot of reactance to it. There's not a lot of inductance or capacitance. As I change frequency, right? So I could, in this band range, I could go from 8.7 to 19 megahertz there. The standing wave ratio, which is essentially a measure of how far our component is, our antenna that this is representing is from 50 ohms. As I change the frequency, our standing wave ratio doesn't actually change at all, right? It's constant at 1.7. It basically says there's a small mismatch between this and purely 50 ohms. That makes sense because this is about, as we saw, about 80 ohms. But, let me turn this off for a second. Let's add some additional capacitance to it. So I'm going to take one of my bins of capacitors and grab, this is a 470 picofarad little ceramic cap here. And this is the beauty of, I thought I smelled something burning there for a second. Never a good thing. Let's just loosen these terminals and we'll put this cap in parallel with our resistor here, and we'll see how that changes things on our meter. Might actually, there's just gunk from the packaging tape on this capacitor. I'm just gonna trim that off real quick. Let's see. Enrico says, I most definitely didn't make any Foon-inspired entries into owning air-to-audio technology. Ooh. My goodness, I do love the Twitter user Foon. Anyone's not following Foon, F-O-O-N-E, they are a fantastic nerd. Doesn't the whiteboard say something about no fire? No. It says no fireballs, but that's a different thing. So let's see here. So this, let's see, what's our SWR now? So now it's up at 7.6, 7.4, just with the addition of that capacitor. As we change our frequency, it only increases until it gets off scale. That's what that H means. So as I decrease my frequency here, so we're down at 16 megahertz, we can see we have our sort of lowest mismatch. Let's go even lower. Let's change back to that low frequency band, and we'll find the sort of frequency where this SWR is lowest. Looks like it's even lower than this. Let's see, can we go low enough? Maybe not. 1.2 frequency as SWR. So it looks like it's sort of minimum. It gets lowest at around 1.7, which makes sense. That's the lowest we saw before with just that resistance. And here, this frequency is at 1.5 megahertz or so, right at the upper end of the AM broadcast band by coincidence. So this is the point where this, the world's worst antenna, this here antenna is resonant. In other words, it has equal amounts of inductance and capacitance. And since inductance and capacitance are opposites at some specific frequency, their reactivity will be the same and opposite and sort of cancel each other out. So at 1.5-ish megahertz, oh yes, Enrico, YouTube chat doesn't allow link posting, sadly. We've tried to work around that before, but we don't have a great workaround. So anyway, so this is one of the things that it's just going way back to like when I was trying sort of poorly to describe impedance matching. This is a part of what we do is take a non-ideal source or non-ideal antenna and add some capacitance or reactance either in series or parallel with it to try and get its reactance at the frequency that we're interested in to be as sort of as close to the reactance as close to 0 and the SWR as close to 1 as we can. We can see here that it thinks we have some reactance. Add spaces to the link, or is the YouTube smart enough for that? I don't know. That's beyond my YouTube knowledge. Worth a try. I don't think it'll penalize you or anything. I just think it won't actually show up. But yeah, so that's the little look at this tool, the RF Analyst, which is some really basic. You can adjust the frequency, you can see the SWR, and then just a real basic reading of the resistance and the reactance there, right? So this is the tool I take out into the field because this is built pretty durably. It does what I need to do, which is tell me, am I going to have a good match to 50 ohms or not? That's all I really care about. For more advanced readings, here's another fun toy. I'll get rid of this guy. I actually think I have to do some cleanup after tonight to make sure all these things get back. But we have the Nano VNA, which is a nifty tool that's come out in the past couple of years. This is a vector network analyzer in a little tiny battery-powered portable firm package. Now, what is a VNA? Well, it's essentially a device with a small RF transmitter in it and a small RF receiver, both on its transmit port and on a second port, that you can use to analyze the reflective and through properties of an RF device. Now, what does all that mean? Well, let me show you. So let me turn this on. Try to find an angle where it's not getting glared out. That's actually not bad. Maybe we'll just... That's better. There we go. So first thing I will have to do is calibrate this. So this is displaying information on what's called a Smith chart, which is a way of displaying impedances, resistances, and reactances sort of on the same display together. But why don't we, let's see here. Let's turn on a channel that has SWR, because that's what we were looking at a moment ago. Channel 0. That's through. Actually, let's just do through signal. Let's do SWR. So I'm going to go into the menu here. I'll go into format, and I will say this yellow trace will display SWR. Now, there's nothing hooked up here, so it's showing the SWR of basically nothing. So let me do a quick calibration sequence here, and then we can sort of play with this like we were playing with the antenna analyzer. So to do is say, okay, it needs to know, it's going to sort of filter out all of the imperfections of the device itself. So I'm going to go into and this is not meant to be a tutorial on how to use this device. There's lots of those on the internet already that are quite good. But let me go into my calibration, just prop this up so we can maintain this nice viewing angle here if we can, or if we can't, then we won't. Let's see here. Oops, sorry. Probably hear that ringing a bit there. What if we... I really want it to be like there. Just stack some more pliers behind it. There we go. Or we'll just hold it. That seems fine. So what I'll do is I'll go into my calibration sequence, and I will first put on my... I guess this is my open test. Let's see, I can put on my open cap. Basically, I need to tell it give it a moment to take its readings when there's nothing connected, when there is a short connected, and when there's a 50 ohm load connected. So I'm going to say this is my open connection, which is just a little cap that literally has nothing inside of it, just so the properties of the cap itself might become important. I have my short connection, which is just like literally metal that's going to bond that center pin to the outer connection. So I screw that in over here on channel 0, and I hit short. And I need my load connection, which is going to be a tiny little 50 ohm resistor inside a little tiny package, and that's what that is. I screw that in, and I hit load, and I am done. And I will save that as calibration 1, and now we're nice and calibrated. So, I'm so not prepared to do a tutorial on a Smith chart, but the gist of it is, because again, we want to represent a very wide range of measurements. Center on this Smith chart is 50 ohms. All the way to the right on the Smith chart, if I take this off, represents an open circuit, an infinite impedance, and all the way to the left represents a short circuit. So if I screw my shorting cap back on, oops, is that my shorting cap or my open cap? That's my open circuit. If I basically short the contacts here, then I move all the way to the left in theory, and that's a short circuit. So we have short circuit, so 0 ohms, 50 ohms, infinite ohms. Area above this center line represents inductive reactance, so we can move up into the inductive world, and area below that center line represents capacitance. So let's do our same 2 demos that we did before with this resistor and capacitor and just see what those look like on the Smith chart. So first we'll just take our nominally 82 ohm resistor, and using this included string of cable. Now this is going to be a little bit, let's see. You know what we should do? So this cable, if we were working at like low frequencies, this cable wouldn't matter. At the frequencies that we're currently calibrated for, which is up to 900 megahertz, that's actually going to really factor into what our analyzer sees. So I'll tell you what we'll do. We'll just go into our stimulus menu here, and I'm actually going to turn our frequency range of interest way down. Let's turn this down to, instead of 900 megahertz, let's go to 50 megahertz. And that's going to be a lot more forgiving in terms of having of cables and adapters and things. I guess there is also a way to calibrate that out, but why don't we do, just for good measure, so because our current range is within the range of our previous frequency, we probably don't necessarily need to recalibrate it, but it's always a good idea to. So there's our open. We'll do our short again, just because I would hate for this demo to become any longer than it is. By being bad. So that's our short, and we'll put our 50 ohm load back on there, and we'll calibrate for load. There we go, and done. Save that as 1 again. Okay, now we're calibrated for this frequency range up to 50 megahertz. So if we attach our resistor here, we will see that, okay, so this is what I was hoping to see. So we can see, I think we can even see the readings on here as we change we use a little thumb wheel on here to change the specific frequency we're looking at. You can see up at the top, the value that we're reading for resistance and reactance is actually changing. So if we read this data down all the way at the bottom of our spectrum at 50 kilohertz, we see that at 50 kilohertz, this device is behaving like a 73 ohm, 600-ish nanohenry device. So it's very slightly inductive at low frequencies. But as we move up in frequency, let's say up to 14 megahertz, so sort of one of our areas of interest, we can see here it's starting to become very slightly capacitive. So probably what's happening is that the windings of wire within this device, remember we said this is a wire-wound resistor, so it's a wire, a very thin wire with resistive material in between it. The actual bits of wire that are close to each other but separated are acting like a little capacitor. And as we go up and up and up in frequency, the effect of that capacitance is going to, let's see, going to decrease actually. It's acting like a smaller and smaller capacitor, I should say. Which on the Smith chart looks like just rotating around that center axis. So now let's put the capacitor in parallel here and see what that does to our measurements. This is a super fun tool. So if I haven't said before, I evangelized for many years, and I still do. If you are interested in working on any kind of AC circuit, and by AC I mean anything that's not DC, anything that changes state, having a cheapy oscilloscope is a really valuable tool. because it really is your eyes into the electronic world. Once you start working at RF, having a VNA, as it turns out, is sort of the same thing. It's your eyes into the world. So, now this is very cool. So now let's go back down to our low frequency, basically almost DC. And we can see at almost DC, we can see we behave basically like a resistor, right? At 50 kilohertz, it's a 72 ohm resistor with a little bit of capacitance. But as we go up and up in frequency, this thing behaves less and less like an ideal resistor. We can see by the time we're at, let's go back up to our 14 megahertz example, we are at about 11 ohms and 886 picofarads is the equivalent series capacitance. And our SWR, we see there, is also climbing. That's that yellow graph there. And SWR, remember, is just a way of representing the mismatch between our transmitter, in this case our measurement device, and our load. So this is a 50 ohm source. The SWR is a representation of how much that source is mismatched to our load on our other end. Now normally, that could be an antenna, that could be some other kind of reactive device. In this case, it's a resistor and a capacitor. But SWR, it's not a straight ratio of the mismatch, it's a calculated value. But the higher the SWR, the more mismatched things are. So as we go up and up and up, we can see that SWR increasing, and we get more and more beyond. Let's see. So our resonant point here, so another resonant point, I guess I should say, is for this demo, with this exact set of connections, is about 20.5 megahertz. So at 20.5 megahertz, this thing, again, looks like a resistance because the inductance of the resistor and the capacitance of the capacitor are balancing each other out at right around that value. As we continue to go up, the inductance starts to dominate. So that by we get to around 50 megahertz, which is the top of the range that we're measuring today, we're once again we're very inductive. We look like a 153 nanohenry inductor. So we have a particularly poor match. One of the takeaways, one of the reasons that the Smith chart is useful, is that the SWR essentially is a measure of how far this measurement point is from the center of our chart, which is where this circle crosses that center line there. And it doesn't really matter in which direction we are separated from it from, right? So here is actually where we're quite close. We have an SWR of 1.45, and we're quite close. We could be quite close, but down here and still have a decent SWR. But whatever is contributing to that mismatch, whether it's a difference in resistance or a difference in impedance or in reactance, whether we're too inductive or too capacitive, that's going to negatively affect our SWR. We actually see up here we're coming back to we're coming back toward the real axis here, which is kind of interesting. Now, some of this, of course, has to do with the fact that we are, again, attached by this short-length cable, and as our frequency increases, this starts to become a more and more significant portion of the wavelength of our RF energy. So really what I should do is do some calibrations to try and calibrate that out, but I'm not going to bother doing that tonight, I think, because I usually mess it up. So that's one of the things that these VNAs can do, is measure, the primary thing they do is measure reactance and impedance across various frequencies. They can also measure the response through a particular device. So right now we're looking at the absorption and reflection coming back from a single channel of this device. We could also hook this up to both sides of, say, a filter or an amplifier and measure the through response from one channel to the other. And because there's a receiver in both that's sort of locked together, we could say, okay, as this moves through the filter, the phase is adjusted like so. We lose 3 dB in the filter, and the filtering characteristics are X, Y, and Z. But that's essentially what that tool is measuring the incoming and outgoing impedance of various circuits. So yeah, super fun toy. The other great thing about this was, I think, $70, which is wild. A VNA, a decent lab quality VNA, is tens of thousands of dollars. A cheapy hobby one used to be still $1,000, and this was like basically an impulse purchase. So it's super delightful tool when you're playing around with RF to have something like this. They also make a spectrum analyzer version, which is meant for not so much transmitting signals out and seeing what happens to them, but absorbing extant signals. Really nice thing if you're building a transmitter, to see what kind of energy it puts out, so you maintain that spectral purity we were talking about. The Nano VNA, or the Nano SA, I think that one is, which is the spectrum analyzer equivalent. Really very cool. Yeah. That's the Nano VNA in a nutshell. It's really quite a nifty device. Here, let's do one more thing. Let's take the take the resistor out of this, and we'll see what a nominally just a capacitor looks like. Although, of course, it's a capacitor on the other side of a wire with some real physical properties to it. So, so we can see here that at low frequencies, my circuit, which, again, includes... let's see, I want to see my capacitance value on the screen here. I've hidden it for myself somehow. Let's see, display, format, log mag, phase delay, Smith. Oh no, I don't want to show two Smith charts. That seems a little bit redundant. We'll go back to showing SWR on that. We will go back to our first trace 1, and we will say we want real imaginary resistance reactance. No, I really want... Not sure why it's gotten rid of my reactance values there, but we can see that currently, although I'm currently waving it about and the connection's a little incorrect, but at a low frequency, it's basically purely resistive. And as we increase in frequency, it's not until we reach about 7 megahertz that it looks purely like a capacitor. And then above a certain frequency, above 20 megahertz, it starts to look like an inductor again. So it looks actually that we were seeing this thing become inductive after a certain frequency. It wasn't the resistor at all. It was this capacitor that was looking like an inductor. And this is one of the cool and wild things about amateur radio is you get to learn stuff like this that, we're used to when we're talking about circuits. You say, okay, you put a resistor here and you put a capacitor there and you draw them with the squiggles on your paper and it's like, okay, well, this is a resistor. It has a resistance. This is a capacitor. It's a perfect capacitor. But in real life, right, we can see that this capacitor, let's say we were using this capacitor to smooth out a power line on a circuit, right? It's pretty common. You put a capacitor between your power rail and ground to help sort of smooth things out, act like a capacitor there. Well, we can see that if the signals we were looking at were, a few kilohertz or a few megahertz, that would be fine. But if the signals of interest, if the noise on our power line was above 20 megahertz, we'd be in big trouble because suddenly this thing isn't actually a capacitor at all. The properties of it, maybe it's the physical leads here, maybe again it's the fact that we have this giant adapter that we haven't accounted for yet. This thing is actually an inductor above a certain frequency. And this is the kind of stuff you run into all the time working with RF, is that like resistors are not a resistor, capacitor is not a capacitor, inductor is a lie. Everything conducts, everything emits radiation. You get into these really squirrely things that I just love playing with and learning about. And this has been a really cool tool for doing that in the past few months that I've had it. So I just wanted to show it off because if you're interested in this kind of thing and playing around and having eyes on circuits, super cool tool. Well, I think that just about does it for my sort of rambly, impromptu update on what I've been working on for the past few weeks as I've been not avoiding you. It's lovely to see you all, especially the new faces and the classic faces. Thank you for coming and hanging out. I just wanted to keep you updated. And I don't know, it's interesting in this weird world of ours. And as I've said before, I don't think of myself as a streamer. I just am a nerd who finds it fun to share these things. I wish I remember talking to my parents growing up, and I remember saying things, we would all say like, I wish I had like one thing I wanted to do, just one thing. Like I have friends from childhood who knew from 7th grade that they wanted to be a doctor, and they went to high school to think about being a doctor, college for doctoring, and now they're doctors, right? They one thing and they're doing it and they love it and it's great. And I want to try everything. I want to build radios, and I want to repair a gramophone, and I want to build a DMX moving light and get a 3D printer and a CNC router and all these things. And that makes it sometimes hard to figure out what like the focus is. And of course, the modern era that we're in, this streaming era, rewards those who have a singular focus. And so there is maybe a pressure that I put on myself to think about like, well, what should this channel be? What is the channel? What is my focus? What is my thing? And more and more I'm finding that I'm happy just like, gathering this community of curious nerds who want to learn about stuff. And I am not at all offended, especially, Enrico, I don't know if you're here anymore, but like people being like, hey, just wanted to pop in and say hi. This topic is not for me or more than I just like have brain space for tonight, which is totally fair. But you talk about have so many half-done projects, Chris, that's absolutely me. I mean, you saw that bin of like, just modules on modules that I played with and mostly finished, then put away. So in any case, this is all just a rambling way of saying like, we have not departed. This is not a pivot. We still have unfinished business in the DMX 3D printed moving light world. We're coming back to that. But you can also expect more, I think, just of updates being like, hey, here's a nerdy thing I'm doing today. Maybe you'll find it interesting. Oh, no, Enrico says he's not here anymore. So Enrico is a paradox. Real shame. But Enrico, we like a paradox here, I think. But yeah, more to come. I hope to just acknowledge that weirdness out loud of when you're watching as a YouTube viewer, I'm always looking for a channel with a focus, and as a nerd who is not a streamer, just putting things out there, I just like sharing my nerddom with y'all, and I appreciate you being here. And it's really fun to even if it's way off the beaten path and not what we normally talk about. It's fun to share those things with you. So thanks for coming by tonight. It's good to see you all, and I hope you're having a wonderful week and staying warm and or cool and or wet and or dry, depending on what your climatic needs are where you are at the moment. I hope you're all staying safe out there, staying hydrated. And yeah, we'll be back, I hope, next week. I hope to continue this a little bit more regularly, although there is a semi-decent chance we'll be hiding with my dog in the bedroom again, so we'll see. Yeah, Broke Both, thanks. It's a pleasure to do these and to be here. If you, thank you. Follow your passions. I love that so much. Yeah. Goodness knows I have enough passions to follow, so we'll keep it going. If you're like, hey, I want a nerd to share this with, you can always find me on Twitter. It's down here at Jeffers Glass. You can leave a voicemail at 815-OH-MALORT. The phones themselves don't ring at the moment. I have a replacement analog telephone adapter to actually hopefully get those phones ringing again. You can follow some more nerdy things at my website, jeff.glass, where my blog is. I put a whole write-up on a big radio outing I had the other weekend. There'll be one up soon about this past weekend, and some other things there. Yeah, a lot going on. But as always, I've been a nerd. Y'all are great, and I will see you, hopefully, if we don't have thunderstorms, next week. Take care, y'all.